So our second speaker is Andreea Alexandru. It's close, not close enough, but what? She graduated in 2015. She got her bachelor from the University of Bucharest in Romania. I'm not going to try to pronounce that either. She's been here since she's a third-year PhD student working with Professor George Papas and Professor Arijat Babai. And she's interested in privacy, control systems, using information theoretic tools, which is what she's going to talk about today. Thank you very much.
Thank you. Well, I'm actually going to use cryptography more than information theory, but that's good. Okay. So yeah, I'm going to talk about privacy-preserving cloud-based quadratic optimization, and this is joint work with Konstantinos Gatsis and George Papas. And I will try to be a bit introductory in the privacy and security issues. So our research lies in the area of large systems with many sensors, such as smart cars, smart building, everything smart. And so the issues there is that there are shrinking sizes, shrinking costs, which means that we have reduced computational capabilities, reduced communication capabilities. So that's why we are looking towards a centralized setting in which we try to outsource the computations to the cloud. But there is a fundamental issue there, which is that of privacy, because the users might refrain from using whatever service we provide because they don't want to give their data in the clear to the cloud. And moreover, maybe the service the cloud provides is also proprietary, so it has some very fancy parameters that should be concealed. Okay, so you are all familiar with problems such as when you have medical databases and you do some statistics on top of them, and you do not want to give the patient's data out there to especially medical insurance companies, or the same when you want to do traffic control, but the drivers don't want to give their locations at all times in order to achieve this result. But however, we're interested in other types of problems where we need privacy, and that's in controlling cyber-physical systems. And so we want to do state estimation in the secure way. We want to do control in a secure way. Also decision-taking with machine learning in a secure way, which means keep the data private and also the result of this computation private. So what these things have in common is that they can be modeled as constrained optimization problems. And moreover, the ones I chose here, they can be modeled as quadratic optimization problems. So in this talk, I'm actually going to address a case of quadratic optimization problems and how to solve it in a secure manner. So what kind of security are we using? We use the cryptographic security definition, which very high level means that after the execution of the protocol, no private information is revealed other than what can be already inferred from the inputs and the outputs of the protocol, which one cannot hide. So we're talking about computationally bounded adversaries, in particular probabilistic polynomial time. And when the security is modeled as a decision problem, this basically means that such an adversary cannot perform better than just negligibly better than a random guess. So basically, this is the definition of computational security that we're going to use. Okay, so having this definition, what we want to do is actually come up with a protocol that preserves the privacy of our optimization problem. There has been work in this area, obviously, but however, many people considered unconstrained problems and use gradient descent on them, which in this case, an iteration of the gradient descent is very easy. So it's not hard to do. There have been also works that consider linear problems, but solve them with simplex method in a secure way. But the simplex method cannot really be generalized to many other problems. In our group, there has been previous work that tried to address the same problem of quadratic optimization with partial homomorphic encryption, but they were revealing sensitive information about the variables, which only guaranteed some sort of conditional privacy of the data. And we will avoid this problem. And there is a complete different kind of work which does not use cryptography, but uses differential privacy. However, the problem here is that you will always have a trade-off between the level of accuracy of the solution and the level of privacy you guarantee. And similar methods, they're called transformation methods, in which basically you try to transform the problem you want to solve in a different one and solve the other one. However, the result of such a problem will always lie in a set, which can be smaller or larger depending on the problem. So you're still revealing some sort of information. OK, so what we want to do is actually try to come up with not come up, but use a scheme which is able to perform the computations directly on the encrypted data. So from this, there are such existing schemes. And I guess the most well-known ones are called fully and somewhat homomorphic encryption schemes, which support both additions and multiplications directly on the encrypted data. However, those are very complex and have a high execution time. There is also the partially counterpart of the same kind of methods, which only support addition or only support multiplication between the encrypted data, but they have the big advantage that they are tractable. And there are also some methods called garbled circuits, which support even more operations than just the polynomial type operations, but they work on Boolean. They work with Boolean arithmetics, which make that in some cases the circuits will have a very large depth and very large complexity. So, OK, we want to achieve this secure protocol, but we also want to do it like in a reasonable amount of time. So this is the reason why we choose the middle version, the partial homomorphic encryption, and we will try to see what algorithm to use that will be enough for what this scheme offers. OK, so let me also talk about this kind of encryption. And the reason why it's called homomorphic is because the decryption primitive is a homomorphism between the space of the messages and the space of the encrypted messages. Also, I'm going to use some definitions, names. Like, we call messages plain texts, and encrypted messages ciphertexts. So I'm going to use these two names, so just you know what they are. OK, so the name of the cryptosystem we're going to use is called PyA. It was developed in 1999. And it's a public key scheme, which means that basically the public key with which you encrypt is available to everybody, but only the party that has access to the secret key is able to decrypt. And let's see how the encryption primitive looks like. So for an integer message, basically the encryption is defined as an exponential. So if we want to achieve addition, this means that the operation between the ciphertext is modular multiplication. So this means that if we do this operation on two ciphertexts, we will achieve a ciphertext that is the encryption of the sum of the messages. And this is what we want. And also we get for free that we can achieve a multiplication by a plain text of an encrypted scheme, which, again, this is an integer. So this means that you just raise your ciphertext to that power. So these are really nice features, but we have to keep in mind that not all operations can be achieved with this sort of scheme. So for example, PyA is a probabilistic scheme because of this thing in encryption, which is a random noise, and which help with its semantic security. But this means that the order between the plain text is not preserved in the ciphertext space. And we will see that we need to be able to do comparison. And it cannot be performed locally by only one party, but it will need, we will need communication to achieve this comparison. OK, and one last definition is the semi-honest model, which means that the parties correctly perform the tasks in the protocol, but however, they are allowed to store the transcript of the messages and try to process these messages in order to find out information of the other parties. So The architecture we considered, as I mentioned, is a centralized one. We have P agents that are owners of the private data, and these agents will encrypt their data, send it to the cloud, which aggregates them, and can also have its own private data. I'm going to show which that data is. And the result of this computation that is outsourced to the cloud has to go to another party called the target. It's easy to think about this, for example, as the agents being sensors, the cloud being a controller, and the target being an actuator. This is one sort of an example. And here I just added some notation. Everything that has cryptographic A belongs to the agents. Everything that has cryptographic C belongs to the cloud. And the target receives X star. And this party is the one that has the secret key. OK, so as I mentioned, we're interested in a quadratic problem, more specifically a strictly convex one. And we also consider linear inequalities. And so these two vectors are private and belong to the agents. And these two matrices belong to the cloud. So when we say we want to achieve privacy for all the users involved, this means that no user can find anything about the other user's data. So for example, the cloud is not allowed to learn anything about X star and is not allowed to learn anything about these two vectors. And similarly for the other parties involved. OK, so yes, I mentioned what the privacy is, but it's important to also consider coalitions between the parties involved. So if you have a number of parties sharing their data together in order to be able to infer some information about the other private data, they are not able to do it with this protocol. OK, so we know many things in optimization theory and many algorithms. So let me make a comparison to see what is the difficulty between using encrypted data and unencrypted data. So in the unencrypted case, basically you have the cloud that aggregates all the data and locally solves it using its fastest available interior point methods. However, when we're working on encrypted data, the cloud can still aggregate the data, but however, it cannot solve it by itself because it's not able to compute any kind of operation on the encrypted data. And secondly, it cannot use any kind of optimization algorithm because the operations are too complex to be made in an encrypted setting. Even multiplication between encrypted data or division is very complicated. So this brings us to our approach, and that I've already hinted to. So we will be using a partially homomorphic encryption scheme on top of gradient methods. And the reason why we chose this particular combination is that for a quadratic problem, the gradient is linear in the encrypted data. So as I mentioned, we work with strictly convex problems, and that's why, because we can use the dual and actually be able to retrieve the primal optimal from the dual optimal. And basically, for any kind of operation that we need to do and we're not able to do it locally, we will use computation. Outsource the computation in an interactive way. OK, so the dual, you guys know how this looks like. From the optimality condition, this is the equation from which we can retrieve the primal optimal from the dual optimum. And again, the reason why we chose to go to the dual is that now the constraints become very easy. So it's just a projection on the positive orthant. So in this case, an iteration of the projected gradient ascent is just the maximum between 0 and the updated dual variable in the direction of the gradient ascent. However, there are more optimality conditions that we need to take in account. And those are the complementary slackness conditions. And that's the reason because we know what the dual variables at optimum mean. They tell us if the primal constraints are satisfied with strict inequality or with equality. So if any of the parties have access to the sign of the optimal dual variables, meaning if it's 0 or strictly positive, then they can use the other optimality conditions to infer some information about the private data. And while in general this doesn't mean you can uniquely identify the private data, you leak some information. You specify some subspace in which it will lie. So this doesn't satisfy that definition of do not leak any information. So the main takeaway from here is that we really need to make this maximization secure in a secure way. So I'm going to describe the flow of the protocol, and then I'm going to go into the details of the steps. So basically, the agents just have to encrypt their data and send it to the cloud. So from their side is minimally computationally intensive. The cloud aggregates the data, the encrypted data, and then it will embark in an iterative and interactive protocol with this party that has the secret key. And basically, this interactive protocol will be the iterations of the gradient descent. Also, sorry, I haven't mentioned this. We pick it as being one of the over the Lipschitz constant of the objective function. So it's going to be known to the cloud because it only depends on the matrices that the cloud has. So this is important because the gradient will be able to be locally computed at the cloud side. And also because the cloud can obtain some sort of information about when this method will, the gradient method will converge. It has some big O of some data, so it can approximate this with a public constant. Okay, so at the end of these k iterations, the cloud will be able to compute the dual optimum and again locally extract the encrypted primal optimum, send it to a target which will be decrypted. Now, what happens inside here? We need two steps. First of all, obtain the comparison, that maximum. And second of all, very importantly, update the dual variable such as neither these two parties know if it was updated with 0 or with the updated iterate in the gradient ascent direction. So as I mentioned, comparison is not possible to be done locally on encrypted data with this partial homomorphic encryption. And well, the main idea is that in the literature, there are protocols such that if you have two parties, each of them with a private value, you can make one of the parties know only the bit, which is 1 if, I don't know, if for example, A is less or equal than B and 0 otherwise. So basically, we can modify this protocol such that between two parties, where one party has both encrypted inputs, only the other target can find out this comparison result bit without this party knowing it. So this achieves only one side of our problem, which is the cloud doesn't know the comparison result, but we also need the target not to know this result. So that's why we have a randomization step before in which basically we randomize the order at each step between the 0 and what we computed. And this also ensures the fact that the target only knows one of them is greater, but doesn't know which one. And the next step, as I mentioned, is how to update mu k plus 1. And what we need to do is to actually use some sort of a one-time pad, which means that you blind your private value with a large noise such that in distribution, this blinded value with a random value of the same size will be computationally indistinguishable. So basically what the cloud will do is it will blind the two inputs, send them to a target, which will pick one of them according to the comparison bit it has. And then we need another step, which is called the refreshing of the ciphertext, because if you just picks one of them and sends it back, then the cloud can simply compare what it sent with what it received. And the refreshing of the ciphertext can be, for example, achieved with adding of a zero encryption, of an encryption of 0. And last step, which I will be happy to talk to you about if you're interested, but here I'm just going to say we use some properties of the pair encryption, which allows us to basically subtract the corresponding noise in order to update the dual variable with the maximum result. Okay, so we are able to prove that this protocol is secure in the semi-honest model. And there are many cryptographic concepts that we're using, so semantic security, computational indistinguishability, and a very important one, which is if you have sub-protocols that are secure and you sequentially compose them, you actually get a secure protocol. Again, I will not go into details, also in the interest of time. The security of our protocol still holds when we have coalitions. But we can only consider coalitions between the cloud and at most P-1 agents, or between the target and at most P-1 agents. And the reason is that if we have a coalition between the cloud and the target, this is an omniscient coalition. They have both the encrypted data and the secret key. Okay, so I also implemented this. And one more thing I want to mention is that the most time-consuming isn't actually computing with the encrypted data, but is the communication. So that's why I added some artificial delay in the network in order to see how bad it is. And the encryption scheme only works on integers. So how to, we get over this issue by using fixed point arithmetic, which means that basically we multiply all our real data with some random number, which in this case we chose to be 2 to the 6, sorry, not random, large number, which we chose this value. So for 32-bit messages, we chose a precision of 16 bits. Okay, and basically what I want to show here is that I chose some random instances of problems. The y-axis is the time, the x-axis is the number of variables, and the color map is the number of constraints. And what I wanted to show is that actually we get reasonable times. It's obviously not real time, and this is not intended to be real time, but it performs well in order of seconds. So to wrap up, we proposed a secure protocol for a quadratic optimization problem, which means be able to keep both the input data private and the output private. And it's very important to minimize the number of iterations, so we can also implement fast gradient methods for this. And we can also extend the protocol to consider other type of constraints. And as a future directions, we want to compare the implementation of this partially homomorphic encryption scheme with a garbled circuit scheme. We actually done it, and our method is better. This is good. And basically, the end goal of this line of research is to be able to do general problems, solve general optimization problems in an encrypted way, also in a reasonable time. So one way of doing is actually, the next problem we're considering is actually when all the data is private to the agent. So also when those matrices are also encrypted, and then this means we will have encrypted multiplication between encrypted data, and we need to come up with a way to go around it. So thank you.
Questions?
Yes.
The challenge in solving general optimization problems is that your gradient is not linear anymore.
Yes. So if we use a partially homomorphic encryption scheme, we can only do linear operations on encrypted. And I mean, if you have, like, I don't know, even a larger degree polynomial, this means that even for computing the gradient, you need multiplications between encrypted data. And while this can be achieved through communication again, it will be expensive. So actually what we're doing is that this is similar to having more data encrypted, so also having the matrices encrypted, because it's basically the same thing. And we're trying to implement this to see a trade-off between how much this communication for multiplication adds. Like, does it make it, I don't know, unreasonably long? Because you can, again, you can use garbage circuits and fully homomorphic encryption that also support multiplications, but those are very, very complex. So it takes of the order of hours to solve even the simpler problem. So basically, we're trying to come up with the simplest solution. That's why we also use gradient methods. Like, just try to come up with the fewest complex operations you need to do in order to achieve the solution. Okay.
So let me ask a question. So you said that the bottleneck, let's say, of this system is actually the communication between the target and the cloud.
Yes.
So if you had a larger number of iterations in the cloud and less communication, would that be better or not?
It will be better, but you cannot do it, right? Because you need this comparison at each iteration. Oh, yes, yes. I mean, again, like if you have, for example, if you have unconstrained, so this means that everything can be done at the cloud because you don't need any comparison. This is super fast. But the problem is this communication, because you need to send ciphertexts. And this ciphertext with this method are n square bits, where n is the basically key length. So, and you use keys over 512 bits. So this is a lot. And that's why you try to reduce communication and do everything locally. But for some operations, you cannot do it.
Okay, let's thank you.
Thank you.